Hi, this video is about coprime numbers. So two integers a and b are coprime if and only if the greatest common divisor of a and b is 1. And if you use the extended Euclidean algorithm, you can find two integers x and y so that you can write one as a linear combination of a and b. So these are two equivalent descriptions of two coprime integers. I'm going to prove three results where we use coprimality. The first one is that if a and b are arbitrary integers and p is a prime number, then if p divides the product of a and b, then p has to divide one of the factors. So, to look at the proof. Well, first, if a or b is 0, then the product is going to be 0 and p is going to divide it. But then either a or b or both is 0, so p divides either a or b or both. So the case where the product is 0 is clear. So what if a and b are both non-zero? Well, since p is a prime, p either divides a or does not. If p divides a, well then this is true and we're done. So suppose p divides the product but does not divide a. That means that the greatest common divisor of p and a is 1, because the only divisors of p is plus minus 1 and plus minus p. So if p is not the greatest common divisor, then 1 is the greatest common divisor. So if p does not divide a, then the greatest common divisor of a and p is 1. That means that a and p are coprime, so I can write p x plus a y equal to 1 for some suitable choices of x and y integers. Now I'll multiply the whole equation by b. So p bx plus a by equals b. Now ab is such that p divides ab. So I can write ab as p times k for an integer k. And that means that left hand side is p times bx plus ky. And this means that p is a factor of b. So p divides b. So if p does not divide a, then p divides b. And that means that this statement is true. The next result states that if a and b are coprime numbers, then if a divides the product of b and c, then a has to divide c. Let's see why that's true. So the proof. Now, since a and b are coprime, I can write 1 as a linear combination of a and b. So there is some x and y, so that ax plus by is 1. Now I'll multiply through by c. So I get acx plus bcy equals c. Then I use that a divides the product bc. That means that bc can be written as a times k for some integer k. So acx plus aky equals c. And now a is a factor on the left hand side. I can write the left hand side as acx plus ky. So this means that a is a factor of c, so a divides c as we want. The third result is that if a and b are non-zero integers and d is the greatest common divisor of the two, then if you divide a and b both by their greatest common divisor, then the two results are coprime numbers. They are integers because D is a divisor of both A and B, so these are integer numbers. But they are also coprime. So why is that true? Well, by the extended Euclidean algorithm, we can write D as a linear combination of A and B. So there is an equation ax plus by equals D, where x and y are integers. Dividing through by D gives me a divided by dx plus b divided by dy equals 1. And that means that 1 is the greatest common divisor of these two, because any other common divisor of these two numbers would be a factor on the left-hand side and had to divide 1. So the only possibility is that 1 is the greatest common divisor of a by d and b by d. So they are coprime.